Greetings and welcome. In today's video, we're going to talk about some properties that the sum and product of roots have for a quadratic equation. So, let's start by defining our first root, which we're going to call s sub 1, or s1, as being defined by the quadratic formula when I have plus the square root, and s2 will be the root in which I have minus the square root. So I've got my two kind of distinct roots here. So let's figure out what would the sum of these two roots look like. Alright, so if I'm adding these two numbers, I guess I'll quickly write those down again. Might as well be super familiar with the quadratic formula. All over 2a, there we are. And I'm adding this one, negative b minus the square root of b squared minus 4ac. And you might be looking at this and thinking, oh my goodness, I hate adding fractions, and these ones look disgusting. But they're actually not that bad. Because first of all, notice that my denominators match. So that's a good thing. And when I add these two things together, since they already are over a common denominator, I could write it like this, negative b plus the square root of b squared minus 4ac plus negative b. Well, I guess I can ignore that minus sign and just write it as minus b minus the square root of b squared minus 4ac, and really all over 2a right now. I mean, this is the most all over 2a you've ever seen. So watch what happens when I combine my like terms. So in my numerator, I've got a negative b and a negative b. So how many b's is that? That's a negative 2b. And then when I try to combine these guys, which are like terms, they're the same radical, right? Same index, and the same radicand. I've got positive one of them and negative one of them. What happens? They cancel. Wow. Huh, that's convenient. So all over 2a, kind of, I guess it's all over in this case, sure, all over 2a. And then the 2's cancel out partially, so, or actually fully in this case. So I get that the sum of my two roots is negative b, or the opposite of b, over a, is s1 plus s2. So that is our sum of roots property. And what are a and b? Once again, a and b are when I have something in this form, ax squared plus bx plus c equals 0. All right, so this a and b is referring to this a and this b. All right. So that's what the sum of the two roots would look like. Let's figure out what would the product of those two look like. So what is s1 times s2? Let's see if we can figure out what happens here. So that would be negative b plus the square root of b squared minus 4ac all over 2a multiplied by negative b minus the square root of b squared minus 4ac all over 2a. And now when you multiply these, I just want to point out that I technically would have to distribute. All right? Vinculums are a type of grouping symbol. These fraction bars indicate that it's this entire numerator multiplied by that entire numerator. Okay? And notice when I multiply those, this is really similar to this. They aren't exactly the same, though, and they're not opposites either. What are they called? Anybody know? They are called conjugates. All right? And when I multiply two conjugates, I get the difference of squares pattern. So let's see how helpful this is going to be for us. So this will be negative b all squared minus this ugly thing all squared. And multiplying the denominators, 2 times 2 is 4, a times a is a squared. Alright, so let's see if we can simplify this a little bit. So negative b all squared is just positive b squared minus, and this square root cancels out with the square perfectly. So it'll be minus parentheses b squared minus 4ac. All right, I'm writing those parentheses there just so I'm very careful with my signage. So distribute this minus sign, and I will get b squared minus b squared plus 4ac all over 4a squared. Now b squared minus b squared, those cancel out. And I'm left with 4ac all over 4a squared. So what cancels out here? Well, the 4's do. And this a cancels out with one of those a's, leaving 1. So what do I get? I get that the product of the roots is equal to c over a. Boy, that did simplify nicely, didn't it? So these are our two properties that we are learning today, the sum of the roots and the product of the roots. So what sort of things can we use these for? Well, I'll show you. I think I've got enough room for an example here. So our example, write a quadratic equation whose roots are, or that has the roots, what if I've got the roots 3/4 and negative 12/5? Okay. Key thing I want to point out here is that it says a quadratic equation. Graphically speaking, just real quick about roots. If I told you that I had a parabola that crossed here and here, there is not just a single parabola that happens to do that. All right, I could have tall, skinny parabolas, right? I could have upside down parabolas. I could have shallow parabolas. There's infinitely many parabolas that pass through those 2 points. Okay, so when it says a quadratic equation, that's literally what it means. It's just kind of a basic quadratic equation that has those, but there are technically infinitely many answers to this. So, well, if I know the two roots, this is my S1, this is my S2, let's figure out what they add to. So S1 plus S2, that's 3/4 plus, I guess I could change that to minus 12/5 right off the bat. Oh, and now here we've got some fraction work. Let's see. So the LCD between 4 and 5 is 20. I have to multiply this one by 4 over 4, and this one by 5 over 5. And I would get 15/20 minus, what's that, 48/20? Yuck. 15 minus 48, what's that, negative 33/20? I believe. Yep. So this is the sum of the two roots. What was the sum of the two roots equal to? Well, it was equal to negative b over a. So here's kind of our first fact that we've got. But that's not our only fact. So I don't want to just say, oh, that a is 20 and b is going to be the 33. Let's wait until we see what the product of the roots is. So S1 times S2, multiplying fractions is often easier than divide or adding them. So let's see, it doesn't look like it can cross cancel, but 3 times negative 12 is negative 36, 4 times 5 is 20. And what is the product of roots equal to? Well, that's equal to c over a. So here are my two facts. So a is common between both of them, and fortunately a happens to be the same in both of those. That won't always be the case. But it looks like I could say a is 20, right? Because a is the denominator in each of these values. Now, if this was like 10 and this one was 20, then you actually can kind of pick. Like I said, this is a quadratic equation. There's infinitely many. you would define A as being one of them, or maybe neither of them, even depending on what the situation is, and then then you'd find like B based off of what your first A was, and to find C, you'd actually have to replace A with whatever you'd called your other one. So if I said A was 10, I'd then plug that in here and solve this equation for C. So I just want to point that out, that can't happen. B, well, the opposite of B is negative 33. So that means B itself must have been 33. And C equals, well, C equals negative 36, right? Because this was positive C equals that, so C is equal to negative 36. So what's an example quadratic that has those points? Well, f of x equals 20x squared plus 33x minus 36 is a quadratic that has those solutions. I guess actually one of the things I could do is have simplified these. Oh wait, no, I lied. This one doesn't simplify. This one would have though. I could have done that. But I would have actually encountered that situation that I was talking about earlier where my a's would have been different. So I actually kind of like these having the same denominator. So I would argue that this is the easiest of quadratics that have those roots or x-intercepts. Or zeros, if you will. Although I could, multiply or divide this all through by any number and get another variation that also has those answers. So here, let me scroll over to this side. Now this is an interesting thing that we're able to do. What about write a quadratic that has roots and what if our roots were 7 minus 3i and 7 plus 3i? What? Now we've solved quadratics that have had imaginary roots, but it's kind of weird to think about, like, how could I take those roots and go backwards to getting a quadratic that has those answers? Well, we'll use the same technique. Let's figure out what is S1 plus S2. So that's 7 minus 3i plus 7 plus 3i. You could put these in parentheses here if you wanted, but it doesn't matter. 7 plus 7 is 14. I almost said 4. I tricked you there, almost. And negative 3i plus 3i, well, those ones would just cancel out. Right? Notice I'm not foiling here because this is plus. All right, just want to point that out. So I get 14, and what is the sum of the two roots equal to? That's negative b over a. So here's kind of our first fact to work with. The next fact comes from the product of the roots. So 7 minus 3i times 7 plus 3i. And when I do have to FOIL out. Or I suppose, hey, I'm multiplying two conjugates. I could use the difference of squares property, right? Because of this. And actually, an interesting thing, perhaps, is, I find it interesting anyway, if I have one imaginary root, the other imaginary root will be its conjugate. It's guaranteed. It's kind of a nice deal. So let's see what this is equal to. Whichever technique we use, I'm going to use this one. So this would be 7 squared minus 3i squared. So that's 21 minus 9i squared. I squared is the same as negative 1. So that's the same as plus 9. So that's 30. And what is S1 times S2 equal to? Oh, that's the same as C over A, right? So looking at these, let's see if we can figure out what are A, B, and C, right? Well, the denominators in both of these are 1, so I guess that's probably the easiest thing I could say is A equals 1, right? B, well, the opposite of B is 14, so B must equal negative 14, right? And C, since A is equal to 1 in both of those, C is equal to 30. And so my equation of a quadratic that has these roots is x squared minus 14x plus 30. And if I solve this by completing the square or quadratic formula, I'll actually find that I get those roots. Let's see. I'm checking my answer now, and it is disagreeing with me. What did I do wrong? Guys, oh my goodness, how embarrassing. Look at what I did. You see what I did? Right here. Ay, mis dedos de los pies. You'll have to put that into Google Translator if you want to figure out what I just said. Let's see, 7 squared, guys, is 49. How did I get 21? I guess it is 2:02 in the morning right now, so cut me some slack. So this would be 58, right? Okay, there we go. So C is 58. 58. There we go. And so if I was to solve this by completing the square or quadratic formula, I actually would be able to get these two roots as my original, or as my answers. And graphically speaking, since my roots are imaginary, that means that this parabola never crosses the x-axis. All right, so that's an interesting outcome there. Now, that's actually one more thing you can do with these problems. Suppose I had this. Suppose I solve 2x squared minus 7x plus 3 equals 0. And I was told to check, let's specifically check using sum and product of roots. So we actually know, 3 ways to solve this? I mean, we could try solving it graphically. It's not the best way. I could see if it's factorable, which actually I think it will be. Oh, how nice. Let's factor this. We haven't factored a problem like this in a little while. 2x squared minus 7x plus 3 equals 0. So this is just a nice quick little review for us. So in order to factor it, well, I noticed that the a value is not 1, so I have to use the AC method. So AC, 2 times 3 is 6. Factors of 6 are 1 and 6, 2 and 3. Which of these, well, this is a positive 6, so which of those add to be 7? Oh, that's 1 and 6. So what do? I split the b term into 2 like terms whose coefficients are the factors we just found. Seriously, I say that so many times. If there was like a Mr. Waddy action figure with pull string like phrases, that would be one of my phrases right there. So let's see. The signs of these, by the way, they multiply to be positive, so they have to be the same. And they add to be negative. And negative 1x minus 6x would in fact combine to be negative 7x. And now what do we do from here? Factor by grouping, yoink, yoink, and x. Yoink, yoink, negative 3. Take that minus sign out with it. So x, 2x minus 1, minus 3 times 2x minus 1. Yay, the parentheses match. I get 2x minus 1 times x minus 3 equals 0. This is not my solution, though. All right, this is factored, but now that I've got two things that multiply to be 0, I can set each one equal to 0 and solve. X minus 3 equals 0. So I get 2x equals 1, x equals a half. And over here, x equals 3. So I just solved this, but now I want to check using the sum and product of roots. Well, so let's do a check. I'll even do a check I'll do it in yellow. Why not? So I'm expecting that S1 plus S2 will equal what? Negative b over a. So if I plug this in, here's my check, sorry. 1/2 plus 3, those were my two roots, or S1, S2, I could have thought of those as, right? Should equal negative b over a. What's b? 7. So that's negative of negative 7. Well, technically, yeah, it was negative 7 technically. and a was 2, right? So let's see if this works out. So half plus 3, I'd have to multiply by 2 over 2. 1 half plus 6 halves is 7 halves. And opposite of -7 is 7. So that checks out. And now let's check out S1 times S2. And what should that equal? C over A. So is 1 half times 3, right? 1 half times 3. Is that equal to C over A? What was C? C was 3, A was 2. Is that equal to 3 halves? Oh boy. Oh boy, you don't say. It seems to work out. So, so there we go. So we can also use this as a nice little check. So, so that's just some properties that we've got for the sum and product of roots. I hope you enjoyed the video, and I'll talk to you guys later. Bye-bye.